How does the first law of thermodynamics relate to mechanical energy conservation? I'm going to argue it's in there somewhere. Even though our intention with establishing and writing the first law of thermodynamics is to apply it to systems where thermal effects are interesting, and generally speaking, when you apply concepts of mechanical energy conservation to a system, it's usually a system where you're emphasizing transformations between different mechanical energy forms, and you generally don't want to have thermal energy forms being created in those kinds of processes. But nevertheless, the ideas are going to be shown to be connected. So if this is the first law of thermodynamics, where the heat applied to a system is equal to the internal energy change of that system plus the work done by the system. Sometimes this is also stated as the capacity of the system to do work. And in that sense, this formula actually is designed to be applied to something like an engine that has fuel, that when that fuel burns, there's heat involved with that. And in fact, if you think back to like maybe a steam engine that's either driven by a wood fire or a coal fire, that's literally what the Q would represent, is the energy transfer from that fire into like a boiler. And then that boiler increases its internal energy, and then that boiler is able to do work. So that this very traditional form of the first law of thermodynamics definitely relates to an application like that. But again, let's see how we can, if we're not thinking about that type of application, if we're thinking about more of a mechanical system that doesn't have like fires and steam and that kind of stuff happening, how might things look? So what I'm going to do mathematically is I'm going to start by subtracting this work from both sides. And one thing we have to remember is that this, again, was the work done by the system. And because it might look weird to have it out here as a subtraction, especially in light of the fact that in mechanics, we often would use work is equal to a change in energy, and it never was negative. But here we've also got heat, right? But something to recognize, if this is the work done by a system, that work is actually equal to negative the work done to that system. So in the sense that if a system does work, that represents a transfer of energy out of that system. If the environment is doing work to that system, that would represent energy being transferred into the system. And if one is positive, the other one would have to be negative. So that's why a formula like that makes sense, which lets me change this to, if you take minus, right, this would look like minus work done to, with that subscript there. But this part here, maybe I didn't need to write it that way. I'm just going to erase some of this stuff, because minus a minus is a plus. So simply we could just say the sum of the heat added to a system plus the work done to that system is equal to the change in energy of that system. This is a pretty big concept here, because it's saying for a system, really the two ways that you can transfer energy into a system is either to add heat to it, or to heat it basically, maybe the more correct way of saying it, or to do mechanical work to it in the sense of a force times displacement. And so if the heat is set to 0, then we get something that might look a little bit familiar, but we've kind of introduced this subscript too. So, I mean, I think the last time we saw this, when we saw work is equal to change in energy, we never had to subscript it before with saying it's the work done to the system. We're doing that now because we want to distinguish it with the first law of thermodynamics version that had this other, the W we started with was really the work done by. In fact, maybe I can add that in here, right? And say this one was by, although if I start with 1, I better subscript everything. So there it is. Just again to really distinguish those two things. But again, this formula was actually something that we could use to argue for mechanical energy conservation. Generally, the argument from here would be to say, if it's a closed system, that means in this context, no work done to that system. And then we always had to still say that the energy changes we were considering were only mechanical, which in reality is only possible if we disallow friction type of forces or any other kind of force that ultimately is based on friction, such as drag forces. Then 0 is equal to delta E implies that 0 is equal to E final minus E initial, which means whatever amount of mechanical energy the system initially started with, that's how much it's going to wind up with, provided none of that is being transformed into thermal energy by the frictional forces I just kind of said verbally have to be disallowed. And as you can see, this all kind of came from the starting point of this first law of thermodynamics, so it really is embedded within the concept. However, as we move forward, the way we're going to apply this is more often than not, this delta E, when we look at thermodynamic type of systems, this delta E is going to represent a change in thermal energy of the system, but there's no like rule in the way the first law of thermodynamics is stated saying that that has to be the case for every single application, but it will wind up making sense for most of the applications that we'd like to use it for. Let's see how this looks in the slide there. It says Q minus W equals delta E, but this W is the work done by the system, as we said, so therefore, I think it said a little differently there, the work done to the system is equal to negative the work done by the system, so then we got Q plus work done to equals delta E, and if there's no heat, that implies W equals delta E, and if as well the work is 0, then delta E is equal to 0. I would say in this slide, I don't think I said enough there about the fact that delta E is equal to 0 could still possibly include internal transformations that would involve thermal energy, so maybe I should have added somewhere there the proviso that there's no friction so that doesn't happen, and that would restrict us to mechanical energy forms.